Okay, sure. Thank you very much. So can you see my screen?
Yes.
Okay, so last time I gave a definition of random walk. So let me briefly remind you the setup. So we have a countable group G endowed with a probability measure mu. And then what we do, we look in the probabilistic terms at products of independent, identically distributed random variables, which are called increments of the random walk, which have as their common distribution this measure mu that determines the random walk. Okay, and so I had first defined the Poisson boundary. We will return to the Poisson boundary a bit later. And at the very end, I had also defined the first quantity invariant of a random walk, which is the rate of escape. In order to define it, I need a certain notion of distance on my group. So I need a left invariant metric. On the group. And then actually, well, since it is left invariant, that's the same as having a way of measuring the distance from the elements of my group to the identity, which is sometimes called the norm. So that's just the identity to our element group. And then one can define the first moment of any measure with respect to this distance. So that's in probabilistic terms, again, just the expectation of the distance from the origin. And then provided first moment is finite, so the measure is not very spread out, then one can define this rate of escape. And there are two definitions. One definition is in average, and the other one is individual along sample paths of our random walk. So according to the first definition, this is just the linear rate of growth of the first moments of the Endfold convolutions of our measure. So the Endfold convolution is just the distribution describing the position of our random walk at time n. So we take the Endfold convolution and take the average distance from the origin, and we normalize it linearly. So that's the definition in average. And one can also do it individually by using Kingman's subadditive ergodic theorem. Here, of course, one should write limit. Namely, for almost every sample path, if we just look at its distance from the origin and divided by n, then we will also have this convergence. Okay, so this invariant of our random walk. And now I will define the another asymptotic invariant, which is asymptotic entropy. Its definition is quite similar. So here, what I start with is a certain quantitative characterization of measures. In the instance of the rate of escape, it was just the distance. And here I will take the informational content of my measure, or in other words, the entropy. So that's the entropy, which is usually called Shannon's entropy, but in fact, it was, of course, in very explicit form, known Shannon to Gibbs and to Boltzmann. Okay, so that's the weighted sum of the logarithms of the weights assigned by our probability measure to the elements of the group. Okay, and well, I don't have time to talk about how important this notion is. It is also not only important, but it is very natural. In fact, in the sense there is the only quantity like this that satisfies two properties. If I take the tensor product of two measures, or just the product, if I take the product of two measures, then the entropy is equal to the sum of the entropies of the factors. That's one property. And the other property is monotonicity, that if I pass from my measure to a certain quotient measure, if I glue together certain widths of the measure, then the entropy will always decrease. Well, actually, there is an equality here. Equality only holds when we don't glue anything together. Okay, and now these two properties imply that if we look at the sequence of the entropies of Endfold convolutions, then this sequence is subadditive. And therefore, in precisely the same way as I did with the rate of escape, now I can define the asymptotic entropy as the linear rate of growth of the entropies of Endfold convolutions. And also, in pretty much the same way as for the rate of growth, one can also define asymptotic entropy individually along the sample paths. Namely, what one has to do, well, one just has to look at the probabilities of typical points. And here, what does it mean? I'm just taking almost every sample path. I'm going along this sample path, and at time n, I'm looking just at the probability, at the probability to be at time n at the point gn. Okay, so I have to take its logarithm divided by n and put minus in front of it. And then, well, this limit also exists, and it coincides with the asymptotic entropy defined by using just the Endfold convolutions, which follows from the subadditive ergodic theorem also in pretty much the same way. So what happens here, again, so let me take the position of my walk at time n plus m. So this is the product of n plus m increments. And then, well, as we did last time, I can split my increments into two groups. So that's, in other words, the product of the position of my random walk at time n, which is Gn, and of the position of a new random walk at time n, which new. The one is obtained by removing the first n increments. So let me put here Tn, G, let's say subscript n. Okay, and therefore now, in order to apply the symbiotic ergodic theorem, what do I have to do? Well, I have to look at the probability to be at this point, which is the product of two elements, at time n plus m. But obviously, one way of getting to this point in n plus m jumps will be the following. First, in n steps, I go to the point Gn, and then in the remaining m steps, I go from the point Gn to this, to its product by this increment on the right. And clearly, this is only one of the possible ways to get to the point Gn plus m in n plus m steps, and therefore the probability to be at time n plus m at point Gn plus m does not exceed the product of the probability of being at time n at the point Gn times the probability of making the remaining jumps in m steps. And this is precisely the Endfold convolution of our measure mu evaluated at the nth point of this new random walk. So it will be, oops, so here I had Gn, and here I will have shifted sample path evaluated at time m. Okay, so therefore I have this convergence as well. And now what can one say about the relationship between these two invariants? So here probably the most important and interesting inequality relating these two quantities is what is often called fundamental inequality. This is the term coined by Vershek, but actually this inequality was first obtained by Guivarch already in 1980. So this fundamental inequality relates three quantities. Two of them I have already defined. That's the rate of escape and the asymptotic entropy. And the third quantity has nothing to do with the random walk. That's something that describes the group, or rather how fast the balls of the metric that we use in defining the rate of escape, how fast these balls grow exponentially. So the third invariant is the asymptotic growth rate, which is obtained in the following way. So one takes the ball of radius n of our metric on the group, takes its cardinality, takes its logarithm, and divides by n, and then takes the limit. So that's the exponential growth rate of our group G. And then the inequality I'm talking about is the following, that actually it's very easy to guess. That's the usual volume inequality for the entropy, that the asymptotic entropy does not exceed the product of the rate of escape times the volume growth. This inequality actually follows from one of the basic properties of the usual, that if we have a finite distribution, then the entropy of this distribution doesn't exceed the logarithm of the cardinality of the support of the distribution. Okay, and here, since we have the convergence almost everywhere in the entropy, it's easy to see that after some pretty obvious manipulations, one arrives at this inequality. Okay, so now let me rewrite it in slightly different ways. I will normalize by the rate of escape, and then this inequality takes this form, that the ratio of the entropy and the rate of escape does not exceed the volume growth of our group. And this inequality actually is very similar to one of the fundamental inequalities of topological dynamics, that the measure entropy of a transformation does not exceed the topological entropy. So here one can draw more analogies, in particular with the famous formula relating the entropy with the Hausdorff dimension and of the invariant measure and the Lyapunov exponent. Actually, it turns out that this formula can be really interpreted close to what I have written on the right here, this inequality between the topological and the measure entropy, in the particular case when we are talking about a free group, or more generally, a hyperbolic group, a Gromov hyperbolic group. So here I don't have time to go into details concerning the definition of a Gromov hyperbolic group. So those who know, they do know, and those who don't, they can always look at the example of the free group. So what happens for the free group? Let me draw its Cayley graph, which is a homogeneous tree, and then this tree has a natural topological boundary. Okay, so that's not F, that's G. G is the topological or hyperbolic boundary. Okay, in this situation, there is a natural metric on this boundary, which is defined in the following way. So suppose that we have two boundary points, then the triangles on our tree, they look like this. So they're not triangles, they are actually tripods. So if we start from the identity, then the geodesic rays coincide up to a certain point, and then they diverge. So the length of this coincidence interval, it's called the confluent. Confluent, or in a fancier way, this is also essentially the Gromov product of the corresponding boundary points. So here we have the boundary points, gamma and gamma prime. Okay, and then I put the distance between gamma and gamma prime to be equal to the exponent to the power minus this confluent. And the confluent is denoted here as Gromov product. So that's the common part of the geodesics going to these 2 points. So that's kind of a natural metric, can be defined not just for free groups. In the case of a free group, our boundary is just a counter set, but can also be defined for general Gromov hyperbolic groups, like for instance, for fundamental groups of negatively curved manifolds. Okay, and then once we have a metric, and we are talking about geometric measure theory, it's natural to ask about the Hausdorff dimension of the boundary. And it turns out that the Hausdorff dimension of the boundary is precisely the exponential growth rate. It is equal to V. And then it turns out that this ratio of the asymptotic entropy and the rate of escape. So it's clear why we are dividing by the rate of escape, because it provides us normalization. It's just normalization. And then it turns out that the Hausdorff dimension of the corresponding limit distribution of the harmonic measure on the boundary, it is equal precisely to the ratio of the rate of escape and the, sorry, not the rate, the other way around, the ratio of the asymptotic entropy and the rate of escape. This result actually, do I have to remind what's the Hausdorff dimension of a measure?
No. It's okay. We know what Hausdorff dimension of the measure.
So this result is actually quite recent. It was only published 2 or 3 years ago, which is due to Ryokichi Tanaka. For trees, it's pretty straightforward, but for general hyperbolic groups, it requires some knowledge of the metric properties of the boundary, but it turns out that it is okay. It is okay. Okay, so that's one analogy with the formula comparing the metric and the topological entropy, and actually one can go a little bit further. Well, in the case of the free group, it's obvious. In the case of a general hyperbolic group, it requires some incantations. That in this situation, we not only have the boundary, but we also have a natural dynamical system on this boundary, which is nothing else but the shift. Indeed, in the case of the free group, infinite words in our generators, they're precisely sequences of symbols. Okay, I'm talking about free group. So that's a set of sequences of symbols. Let's say A1, A2, and so on, where these letters A, I belong to the set of generators and the inverses of our groups. So this is precisely what is called subshift of finite type, or actually in this situation, I think old Soviet terminology is better. It is also called a logical Markov chain. So here we have the admissibility rule, which tells us that two consecutive letters shouldn't kill each other. Okay, and then here we have the natural shift. And of course, it turns out that the Hausdorff dimension of the boundary is nothing else than the topological entropy of this shift. And it turns out that the ratio of the asymptotic entropy and the rate of escape can also be interpreted as the metric entropy, as the metric entropy of an appropriate invariant measure. So what is this invariant measure? A priori, we only have the measure on the boundary, which comes from our random walk. That's our heating distribution. In its this measure itself is not necessarily invariant with respect to this symbolic shift, but one can always modify it. There is always an equivalent measure which makes it invariant. So let me write it down. So if the support of our measure mu is finite, then the harmonic measure mu is actually a Gibbs measure. Is a Gibbs measure. And as such, it is equivalent to an invariant measure. So here, sometimes we find Gibbs measures as the ones which are invariant and have certain properties. Here, to an invariant measure, it has noted by M, and then the topological, the measure entropy of this invariant measure is equal precisely to this ratio. Okay, so are there any questions about this invariant?
So this measure theoretic entropy probably could be defined also as in terms of the critical exponent for the Poincare series or something. So you should sum up the words with certain weights and calculate the rate. Can it be interpreted in such a way?
Okay, in principle, it can. So here, okay, let me move to the next page. One can indeed do this by using our old friend, the green kernel. So let's simply the measure mu is symmetric.
So I think that we
sorry?
No, just lost you for a second, but it's okay. Now it is okay.
So as usual, the green kernel is the sum of the of all the Endfold convolutions. Applicative. So if we have a geodesic, then, okay, so what happens here? Okay, let's say this is just G1, this is the product G1 times G2, and then the green product, sorry, the green function of the product G1 times G2 is equivalent to the product of the green functions at the points G1 and G2. Okay. And it means, therefore, that if I pass to the logarithm with the minus sign of the green kernel, then I can consider as a distance between 2 points, G1 and G2. Okay, and then if one applies this Patterson technology to this distance, or one can do it actually, because for applying the Patterson construction, in principle, one doesn't really need a metric. One only needs a kernel with certain nice properties. So one can do it directly with the green function. So if one applies the Patterson construction to the green function, then indeed one obtains precisely the same harmonic measure at infinity as the Patterson measure.
And
okay, so yeah.
And the exponent for the Patterson construction will be the Hausdorff dimension of this measure, I guess. So
the exponent for the Patterson construction will be the asymptotic entropy. So okay, so in this case, the rate of escape with respect to the green distance will coincide with the asymptotic entropy, 1. So it will be scaled in such a way that it will be equal 1. Because when we do it for having a certain metric from the beginning, then we have to take into account the topological entropy, the growth rate, which is a constant. But here, since everything is adapted to our random walk, this normalizing constant, this volume entropy, will asymptotically be equal 1. Okay, so now what are the questions here? So there are 2 questions. One is, since we have inequality, one can ask about when it holds as equality. So that's the first question. And this question actually also has an interpretation in terms very well known in more classical analysis. That's essentially the question about measure class of the harmonic measure. So since we know that the harmonic measure is Gibbs, in this situation, when we know that it is Gibbs, this coincidence is just equivalent to the coincidence of the measure class of the harmonic measure. So in the Gibbs case, it just means that the harmonic measure is equivalent to the Hausdorff measure. Or in other words, the Patterson measure arising from the distance. And of course, this question arises in various areas. The question of singularity or equivalence of various natural measures, and it is notoriously difficult. is notoriously difficult. So for instance, when talking about random walks, widely open current problem is the following. Suppose that we have the fundamental group of a negatively curved manifold, or let it be just constant curvature surface in dimension 2. Okay, then the question is whether the harmonic measure of any finitely supported random walk is actually singular with respect to the Lebesgue measure class at infinity. Problem. Our group is the fundamental group of a negatively curved manifold. Of constant curvature. The question is whether if our random walk is finitely supported, then the harmonic measure is always singular with respect to the smooth boundary measure. So for a while, I had thought that this would be the case also if our random walk is not necessarily discrete, is not necessarily supported by a discrete subgroup, but now there are several examples showing that this is not true. So one can approximate the uniform measure at infinity by a certain finitely supported random walk, but in all these examples, the group generated by the support of our walk is not discrete. Okay, so that's one question related to this inequality, and the other question
maybe let me mention
relates to
people here who sort of many of them work in holomorphic dynamics. There is a similar question in holomorphic dynamics.
Yeah, of course. Well, that's what I'm hinting at. Yeah.
You're going to talk about this, or
no?
Then let me mention those. Just let us consider Z squared plus C, where C is outside of the Mandelbrot set. So the Julia set is a Cantor set. So, and the conjecture, old conjecture that if we put harmonic measure on this Cantor set, then it is singular with respect to Hausdorff measure on this Cantor set. It's an open question. So it's very easily to state conjecture, but so unsolved.
Yeah, so the general consideration, of course, is that if we have two measures coming from two different structures, like for instance, in my situation, one comes from random walk, the other one comes from the hyperbolic structure, then the coincidence of these measures cannot be just a random incident, but it should imply something serious about interrelation between these structures. But this question is there are other instances in this in which this question can be naturally formulated, and usually it's quite difficult. Okay, so that's one question which arises from looking at the fundamental inequality. The other question is the following. What's the meaning of the left-hand side of this inequality being 0? So, of course, by looking at this inequality, we can conclude that the both vanishing of the rate of escape and or of the asymptotic entropy Each of them separately implies that the asymptotic entropy is equal to 0. And well, in terms of this Hausdorff dimension, this then would mean that we are dealing with a measure whose Hausdorff dimension is 0, and in the context of symbolic dynamics, it imposes significant restrictions on the measures that one obtains. It turns out that in the context of random walks, vanishing of the asymptotic entropy actually has even much clearer interpretation. And now I have to return to the qualitative part of the theory, which I was already discussing during the first lecture. Namely, it turns out that assuming that the entropy of my distribution is finite, then under this condition, vanishing of the asymptotic entropy turns out to be equivalent to triviality of the Poisson boundary, which I had defined. So here, on the left-hand side, we have a quantitative invariant of our random walk, and on the right-hand side, we have a qualitative property.
So Vadim, write that it's equal to 0.
Huh?
You missed that it's equal to 0.
And
Entropy equal to 0.
So let me remind the definition of Poisson boundary. So we were considering the space of sample paths endowed with the corresponding probability measure. And there we consider the following natural equivalence relation. We say that two sample paths are equivalent if they coincide starting from certain moments. These moments may be different, therefore up to a certain shift. So this is our equivalence relation. And then one takes the quotient of this path space by the measurable envelope of this equivalence relation. In other words, the maximal quotient of the path space, which is on one hand still reasonable, is measurable, and on the other hand, such that it glues together all the classes of our equivalence relation. Okay, so that's our equivalence relation, and then I take the quotient of the path space by this equivalence relation. And as I explained last time, the Poisson boundary is responsible for presentation of bounded harmonic functions, and therefore we obtain that vanishing of entropy is also equivalent to the Liouville property. Well, actually, nowadays it's common to call this result Liouville theorem, since, well, at least, and therefore Liouville property. But in fact, first it was proved by Cauchy, as many other things. And actually in much greater generality, because Liouville really proved it for arbitrary bounded functions, whereas, Cauchy proved it for arbitrary bounded functions, whereas Liouville only proved it for doubly periodic functions, which by today's standards is completely obvious. No non-constant.
But all this happened in the analytic setting anyway.
In the analytic setting, for actually it was for holomorphic functions, for bounded holomorphic functions, and then for harmonic functions, probably it was done first by Picard. So it's actually quite interesting. Nowadays, all the sources are available, so one can find several notes of Cauchy where he bitterly complains about losing his priority to Liouville. And according to Mittag Löffler, Liouville, he didn't like that Cauchy published that much, and he referred to his publishing activity as mathematical diarrhea. So the the habits didn't change much. Non-constant bounded harmonic functions.
And
yeah,
who translated all that to the probabilistic language?
To probabilistic language, I think the credit should be given in the first place to Doob.
So it is
Because well, there was also simultaneous work of Feller, but I think it was Doob who understood it, well, in the way we understand it nowadays, let's say. Because Doob, actually, he was the first essentially to understand that one shouldn't mix topology and probability, which probabilists nowadays still have a hard time to accept, which is why they like to foray into the area of topology, which is warranted. Okay, so now what is important for me is not just this Liouville property, which is equivalent to vanishing of the entropy, but also consequence of this Liouville property, because the Liouville property for random walks, and here I should rather refer to arbitrary Markov chain. So suppose that we have a general Markov chain, let's say, with a countable state space. Then Markov chain is Liouville. Well, in the same way as for random walks on groups, there are no bounded harmonic functions, or the Poisson boundary is trivial, if and only if it's the transition probabilities of this Markov chain have very, very natural properties. This property is the following. Let's note by pi xn, the n-step transition probability issued from the point x. Okay, so pi x1 is just one-step transition probability, and then when I iterate my chain, well, I arrive at n-step transition probability. And this property essentially is the following. The Liouville property is equivalent to the asymptotic independence of these n-step transition probabilities of the original state. And of course, if this property holds, then clearly we have the Liouville property. Why? So if we have a bounded harmonic function, then, well, it satisfies the mean value property, not just with the respect to one-step transition probabilities, but also with respect to n-step transition probabilities. And therefore, the value of this harmonic function at the point x is the result of averaging our function f with respect to n-step transition probability. And in the same way, the value at any other point is the result of averaging with respect to n-step transition probabilities issued from this other point. But since these two measures almost coincide, they're almost the same in the total variation distance, then since our function is bounded, which is where it also comes useful, in the limit, we obtain that these values are the same. So that's how one proves that this asymptotic invariance implies the Liouville property. And in the opposite direction, it's actually also not very difficult if one does it right way. Okay, so now this property, asymptotic independence of the initial state, has very natural and very nice interpretation for random walks on groups. Because in our case, the transition probabilities are invariant with respect to the action of the group on itself by translations. And therefore, if we issue our random walk from an arbitrary point, now I switch from X to G, because we are on a group. So n-step transition probability from an arbitrary point G is nothing else than the result of the translation by G of the n-step transition probability issued from the identity. And this is the Endfold convolution of our measure. Okay, so in other words, for random walks, this Liouville property means precisely that the sequence of the Endfold convolutions of our measure is asymptotically invariant. So this difference between my original sequence and its translated by any group element goes to 0. And if in this property, instead of Endfold convolutions, I put just an arbitrary sequence of measures, then what gives me is precisely the definition of an amenable group. So a group is amenable if and only if there exists a sequence of probability measures which are asymptotically invariant. This is actually the most natural definition of amenability if you want to verify it. Of course, there is also the original definition of amenability given by von Neumann in terms of existence of an invariant mean on a group. So von Neumann came to this definition by analyzing the Hausdorff-Banach-Tarski paradox, why on certain groups there are invariant means and why on certain other ones, on certain other groups, there are none. So what is an invariant mean? An invariant mean, as opposed to a measure, is a finitely additive measure. The finitely additive measure. One of the problems of the foundations of the measure theory was the question about what happens if one forgets about the countable additivity assumption and looks just about finitely additive measures. Okay, so a group, according to von Neumann, is called amenable if and only if it has an invariant mean, an invariant finitely additive measure defined on all subsets. Okay, so this is the definition, the one I have given, which is much better than von Neumann's definition because it is constructive. Here we are dealing with very constructive objects. And for instance, for proving amenability of the group of integers, by using this asymptotic definition, the most natural thing is just to look at the sequence of the Cesare averages, which provides precisely an asymptotically invariant mean in this sense. And since I'm talking about amenability, I have to say that there is yet another definition of amenability in terms of a fixed point property. That's what one obtains when applying amenability. So that's the most important application of amenability. Okay, so now this is important qualitative property of the group. And now what do we have? So as I have just said, we know that if the asymptotic entropy is equal to 0, we know that this is the same as the Poisson boundary being trivial. And these two equivalent properties, well, equivalent only assuming that our measure has finite entropy, they imply that the group is amenable. Okay, now, well, in the opposite direction, one can prove that conversely, if G is amenable, then there exists a measure mu with a trivial boundary. So this was conjectured by Furstenberg and later proved by Vershik and myself. And there is a quite new result, which in a sense fully completes the picture. That's the question about the groups for which the Poisson boundary is always trivial. So let me formulate it just for supported group. So that's a recent result of 4 offers. What's alphabetic order? Yeah, fish. Hartmann. Oops. Yeah. Okay. So, yeah, indeed, I'm over time already. Yeah, so these 4 offers, they proved that they characterized the class of groups for which the Poisson boundary can be non-trivial. So we know already that it is always non-trivial on non-amenable groups. However, the question is, what are the amenable groups for which there is a measure with with non-trivial Poisson boundary? So here, what are amenable groups? The most standard examples are abelian and nilpotent groups. And then further, there are solvable groups and so on. Now, for abelian and nilpotent groups, the Poisson boundary is trivial, always. And they proved that if we are talking about finitely generated groups, then that's essentially the only class of groups for which the boundary is always trivial. On any other group, one can always find a measure with a non-trivial boundary. Okay, so now what I want to do next is the following. So next time I will, as promised, turn to self-similar groups. So first I will say a couple of words about what happens with these boundaries and with the asymptotic invariants under the elementary structure operations. So when one passes from a group, let's say, to its product by itself, or if one passes to a finite index subgroup. And then I will talk about how random walks behave for self-similar groups, and what can one say about their self-similarity? Okay, so that's, I think, it for today.
Questions or comments?
What happens if you don't assume that the group is countable? Which of the results which you presented remain correct?
Okay, if the group is not countable, first of all, you have to specify in which category you consider your group. So I presume you want it to be, because you see, for instance, von Neumann, he, in his definition of amenability, he didn't care about topological groups. So it was considered, he defined amenability just of an abstract group, be it or not. So if you want to talk about topological groups, then, well, the next step would be to assume that it is locally fine, sorry, locally compact, not locally fine. Well, that's the same in the topological category. Okay, and then here the main issue is actually whether your transition probabilities are singular or not. Because here, let me just give an example. Suppose that we have a compact group. Let's say just a group of rotations of the three-dimensional space, for instance, just a group SO3. This group is compact, and therefore, on this compact group, of course, one cannot have any reasonable boundary behavior, any reasonable harmonic functions. Reasonable, I mean continuous or measurable. On the other hand, then it is not amenable. That's precisely the origin of the Banach, of the, I should add, Hausdorff. This paradox is essentially due to Hausdorff. The origin of Hausdorff-Banach-Tarski paradox. Or one can make it even more palpable, namely there is a free group sitting inside the group of rotations. Okay, and now, well, one can look at a random walk on this free group, and it would have a very rich boundary behavior. However, we won't see this boundary behavior from the point of view of the ambient group. And the problem here is the incompatibility of two different measurable structures. Structure of the ambient group, which is nice, and the structure of this free subgroup, which is not written. And in principle, if you are ready to consider arbitrary measures on your group, then in particular, you may also consider just a countably supported measure. And then, of course, the properties of your random walk will crucially depend on how nice is the group generated by this support. If it is a discrete subgroup, then it will be more or less the same as on the ambient group. However, if it is not a discrete subgroup, it may differ quite significantly.
Do you need your measure to be supported on a symmetric set, or for the
no, not at all, not at all. In this theory, because you see, I had mentioned that last time, this is L infinity theory of random walks. So here symmetry doesn't really play an important role. So the overwhelming majority of the results doesn't require symmetry. So it can either be replaced by certain centering assumption or something like this.
Other
I
questions?
have a question. Sorry, I have a question. So this problem that you said about absolute continuity of the harmonic measure for groups coming from the fundamental group of hyperbolic surfaces, what is the state of the art in that? What is known?
Okay, what is known is the following. it is actually easier when the group is not co-compact, when it is a non-uniform lattice, for instance, when the fundamental domain has cusps. In this case, it is known that the harmonic measure will be singular, and the reason for that is more or less the same as in the following situation. So if you look at the continued fractions, then, well, there is a nice absolutely continuous invariant measure, which is the Gauss measure. But one can also consider the corresponding random walks, which lead to infinite continued fractions. And there it turns out that the harmonic measures of these random walks, they will be singular. The reason being that the Gauss measure, it has a very long tail. It has very long tail. If you look at the distribution of the single positions in the continued fraction, then this distribution doesn't have a finite first moment. Whereas if you do random walk, finitely supported random walk, then you have to switch, move to the next level of the continued fraction sufficiently fast. And therefore, you won't have enough time to accumulate heavy tails for these one-dimensional distributions. So that's more or less the reason why in the presence of cusps, the harmonic measure will be singular. But in what concerns co-compact case, it's actually completely open. It's completely open.
I see. Thank you. Do you have a reference for that?
Reference. Okay, so there were actually seven. Well, not right away. So there were a lot of people working on that. So Macmillan, for instance, did numerical experiments at some stage, suggesting that the harmonic measure might be absolutely continuous, as I had said, in the case when the group generated by the support is not discrete. And then there were results actually by Bourgain, by late Bourgain, and also by Polycott. I think it was in collaboration with someone.
I see. Okay, thank you.
But there, once again, in all this, and that's actually not that surprising, because ultimately, if we look at the just the unit interval, the Lebesgue measure on the unit interval can be also presented as the harmonic measure, right, of a certain, just of a natural iterated function system. But the point is that the rising groups, they are not discrete. They are not discrete.
So when you formulated this entropy criterion, I guess, by Vershik and yourselves, you said that it's more or less obvious that from zero entropy, it follows that the boundary should be trivial. Can you elaborate a little bit? So how obvious is that?
Oh, yeah. Okay, well, I'm not sure my mouse works. Okay, so the way it works, well, actually, I can even try to do it with bare hands. Okay, so the idea is it's really based on the information considerations. And here one should keep in mind that this entropy, the asymptotic entropy, is a very close analog of the Shannon entropy. Entropy meaning the entropy of a symbolic dynamical system. Mm-hmm. And therefore, the Shannon entropy, there is a well-known expression of this asymptotic entropy as the conditional entropy of the first coordinate with respect to
the tail.
With respect to the tail, yeah. And here one has to do the same, namely one has to look conditional entropy of the first increment of the random walk with respect to the tail, with respect to the Poisson boundary. And then actually everything becomes very nice because from the informational point of view, that's also a very natural thing. So you are talking about the mutual information of the first coordinate of the random walk and its behavior infinity. So it's all very natural. And then, well, one can write this entropy. There are classical results about the continuity of information. And then when we write this limit quantity, so the mutual information of the first step with respect to the infinite future, we can write it as a limit of the mutual information of the first step with respect to the time n future. And this mutual information is nothing than the increment of the convolution entropy. That's the difference between the n step and n-1 step entropies of the n step and n-1 step convolutions. So if done properly, it's really very, very natural. So, and then one arrives at what? So that triviality of the vanishing of the asymptotic entropy means that the first increment is independent of the infinite future. And the same works for any number of increments, and then it means that this infinite future is independent of everything, and therefore it must be trivial.
Okay, thanks. It's well, does not immediately follow from general principles. I guess there is something to do.
Well, actually, what is interesting and what hasn't been done so far is actually to find a common viewpoint which would cover, which would contain simultaneously this asymptotic entropy and the entropy of, okay, I don't want to talk about entropy of dynamical systems because here I really want to talk just about entropies of symbolic systems in the presence of a generating partition. So, yeah, it was a long sentence. So once again, it would be nice to find a common approach both to the entropy of symbolic dynamical systems and entropy of random walks on groups.
Yeah. Okay.
If not, let's thank the speaker again.
Thank you.
Okay, Vadim.
Спасибо.